Of parametric equations and plane curves. Parametrics allow us to take an ordinary function and write it in terms of an additional variable that we call a parameter. I'll get to that in a minute, but plane curves are paths of motions, or motion. Up until now, you studied equations with two variables, x and y, whose graphs can be used to describe the path of an object or position of an object. We can use those equations to describe where an object's been or is going, but not when it will be at a particular location. All right. To determine when an object is at a certain location, we need a third variable called a parameter, where the variables x and y describing the location of an object become functions of the parameter themselves. So we're going to focus specifically on what's called curvilinear motion. All right. That's a particular path that lives in this consistent vertical plane. So if you throw an object in the air, that object could go in a variety of different directions. But, like with things like wind resistance, or even, like a major league pitcher throwing a curveball, it may not travel in the same vertical plane. It may shift horizontally, all right? What we're going to do is only focus on the instances where it lives in the same vertical plane. So I created a quick demonstration of what that would look like using GeoGebra. So you don't need to really worry about the commands on the left-hand side. It's really just this. So you have a curve. Now we know what a curve would look like if it were in an XY plane, right? But what I'm saying is that this object is being thrown in the air and living in the same vertical plane. All right, so this would be an instance where it lives in the same vertical plane. It doesn't deviate by going to the left or to the right. All right, so if I move my plane, the curve moves along with it. All right, so regardless of where I go, that curve, and I can change the perspective here, that curve is traveling along with the plane. All right. So what we want to be able to do is learn how to come up with these sorts of equations that not only involve position but also incorporate a parameter of time. All right. So it's one thing to have a parabola to show where an object was in the air. It's another thing to show when it's at that moment. All right, or when it reaches a particular location in the air, what moment that occurs at. All right, so I gave an example here of a rectangular equation. So I actually took this, this was just a screen grab of what I just showed you, but I took that and I put it in the XY plane, gave it a little scale. This is the equation y equals -1/72 x squared plus x. All right, we could just pop that into Desmos real quick. If I could find my calculator. All right, go back to that. So I'll say f of x instead of y is equal to -1/72. We'll say x squared plus x. All right, now in terms of a domain and range, could be better. All right, so I'm going to adjust my window here. I don't really need too much negative. I mean, that -1.113 isn't really hurting anyone, so let me go out to like 100. Now we're looking at something a little bit more reasonable. All right, we don't really need to go up too high. All right, we don't have to go out too far. It looks like we have an x-intercept here at 72. All right, so maybe like go out to 80. And for this one, go out like 25 maybe. Give us ourselves a little bit of wiggle room. You're like a -1 here. It didn't really improve the situation too much, but I mean, it gives a good sense of what the path of the object would be. All right. So after it has traveled 20 feet horizontally, it will have traveled in the air 14.444 feet, right? Assuming that it's measured in feet. And I mean, That's an assumption. We don't know that that's true, but I'm just assigning some sort of unit to it, some sort of relatable unit. All right. So we got the path. I just don't know when it's going to be at, let's say, at its maximum height. All right. Let's say it is feet. After it's traveled a horizontal distance of 36 feet, it's got an elevation or an altitude of 18 feet, but I don't know what moment in time that would happen. Right? Is this like an hour later? Is it like a second later? What are we talking about? Right? That's where parametrics come into play. All right, so for this motion problem, x and y are continuous functions of t. All right, and the resulting path is a plane curve. All right. Now, I put the recall in there that a continuous function is, and I gave the simplistic definition, one whose graph can be traced without lifting the pencil from the paper. But, we know that there's way more complicated ways to discuss continuity, but just for simplicity's sake, we're just going to go with that definition. So we need to parameterize this equation in terms of time. In doing so, we arrive at a parametric pair of equations, each representing a dimension of position as a function of time. Generally, the parameterization relationship comes through either data collection or some known fact. Like, for example, in this case, I'm going to just tell you that the object is moving at a horizontal velocity of 20 meters per second, right? And that the rate of change is constant. Right? That has to come from somewhere. Like, how do we know that? Did somebody put a stopwatch on it? Is it some known fact? Like what are we working with here? But we do need to have access to that information, otherwise it's a non-starter, right? So what I would say here is, again, we know velocity is equal to distance over time. Now they're saying it's got a horizontal distance, all right? So that horizontal distance is dependent on time. So I would let d equal x of t. All right, my t is unknown, but they're telling us the velocity is 20 meters per second. So I could say, just based off of this relationship, that 20 is equal to x of t over t. Now just be careful. This is x of t. It's not x times t. Doesn't matter what level I teach this problem to or this type of technique to. There's always this inclination to say, oh, cancel the t's. X is equal to 20. Well, that's not the case. All right? It's x of t. We need a function of x in terms of time. If I solve this for x of t, so I want to get this alone, I would cross multiply or just multiply both sides by t. I would get x of t is equal to 20t. All right? So that's the first part of my parametric pair. Nice alliteration there. All right, so 20t. Now, we have a relationship between y and x. If I know that x is a function of time, then I can actually go up to my rectangular equation here. All right? I know that y is also going to be a function of time. I can replace every one of these x's, because x again is a function of time. I could write this as y of t is equal to negative x of t squared over 72 plus x of t. Keep wanting to put the parentheses first. All right, but even still, we know, because we just discovered it here, that x of t is really 20t. So negative 20t squared over 72 plus 20t. All right, oh, sorry, it's off the page. Apologies. I'm going to actually smidge that down a little bit anyway. All right, so, it keeps wanting to default to that. All right, so since we know x is a function of time and y is a function of time, I took my y and replaced it with a y of t. I took my x's and replaced those with x of t's. But since we knew that x of t was equal to 20t, I could replace each one of my x of t's with a 20t. All right. So on top, I'm going to get 400t squared over, I'll have a 72 on the bottom, negated, plus 20t. All right. So that's going to be, again, negative 400, if I could get my pen to work, negative 400 t squared, poor quality squared, over 72 plus 20t. Now we could simplify also. Just a quick computation here. Where'd that come from? Yeah, so alpha y equals, pop in the 400, just for the sake of straight up laziness, let the calculator reduce for me. 50 over 9. All right, so negative 50 over 9t squared plus 20t. So that's my parametric pair, and together those will give me the same path but now incorporate an element of time. All right. So we could pop that into Desmos in a sec, but we could also think about our parametric equation as being an ordered pair. I said it's a parametric pair, but it's an ordered pair. Any coordinate in space can be represented by x comma y. But if x is a function of time and y is a function of time, then we could also represent a coordinate in space by x of t comma y of t. So that allows us to make really a variable set of coordinates, which is actually kind of cool to think about. Just resizing a little bit more. Yeah, man. So I could look at this as an ordered pair of 20t, comma, negative 50 over 9 t squared plus 20t. And again, it's going off the grid. I don't know why. So this would be my parametric pair, and it would be written as a function of time. So I would call this f of t instead of f of x. It's a function of time. So f of t is equal to this parametric pair, which I can actually just pop into Desmos now, and it'll show me the curve too, and it'll even do math. So let me just pop that bad boy in there for you. All right, so see, we have this original curve there, but now I'm going to put in the 20t comma blah blah blah. So let's do that. I'm going to turn this one off for a sec. So I'm going to pop in 20t 20t. It asks initially if I want a slider. I don't, because I want to treat t as variable. All right, so I just kind of stay the course here and keep typing. Negative, what was it, 50 over 9 t squared plus 20t. All right, now you see here, it's like, well, it kind of looks like kind of a curve, sort of a curve. It's not quite what I wanted. If I click on this, you see it's only part of what I wanted here, but you also see the domain is only going from 0 to 1. All right, if time is measured in seconds, then this would be saying from time t equals 0 seconds to 1 second later. So this is telling me that at the 1 second mark, we're at this location, which is like, what, 14 and a half? But maybe I want to go more. So I can go up to like 5, for example. Now that gives me way too much. So maybe I'll go to A and then allow for a slider. I really don't need to go below 0, so I take my parameter, my low parameter, and if I have my slider, I can start to really sort of simulate how this is going to go. And it's at 3.6 where it looks like it would hit the surface there. All right, so you get a little better idea when you do that, but this would be the parametric curve. This is the function itself, but this one is dependent on time. So now I know the position at any moment in time. Is come up with a way in which we can get the coordinates, because if I have to plot this on paper, I'll need that information. So what I'm going to do is take this ordered pair and define it as some function g of t. All right, which at first glance doesn't seem to really do anything, but if I evaluate my g function at some point A and click on label, then I can slide my slider and it'll report out the ordered pair at each point. All right, now if I want to, so I don't manipulate the actual shape of the curve, I can call this some other constant C, so that this can be whatever, or consistent with whatever the domain is, but then I can manipulate the point throughout that domain. All right, so I just probably wouldn't want to go beyond the domain that I'm establishing for A, but it is possible to do that. So I can go from -10 to 10. I can do this, from -10 to 10. All right, and so prior to that value, so going from 0 to whatever the A value is, I'd say instead of going from 0 to A, I'd say go from -10 to A. You can kind of play around with that, and you see that it gives us a little bit more room on the negative side, depending on what the circumstances are. Because this is a projectile, but it could very well be a projectile that starts below ground or something like that. All right, but then I can take my point and have it go beyond that path or beyond that domain also. Now, the next part of this is actually having us create graphs of other types of functions. Now, that's actually pretty straightforward, because if you're given the function, you can just type it in and grab the points, just like we did. All right? So you just want to be able to account for the domain that you're given. All right? So I'll just do it on this Desmos. So open paren, we're looking at t squared minus 4 comma 2t. You see the domain that's indicated there goes from 0 to 1, but I want mine to go from -2 to 3. All right. Now, if I take this, duplicate it, and call it something like g of t, I haven't, for this Desmos, I haven't used f yet, so I could call it f of t if I want, but then create an evaluation at some constant c, add that slider, and pop on the labels, I'll get my coordinates. All right, so that's kind of nice at the particular values of t that I care about. So again, I'm only interested in -3 to 2. Going by ones. I'm sorry, I got that backwards. -2 to 3, going by ones. So if I slide my slider at -2, I have coordinates 0, -4. So x value 0, y value -4. Go to a 1, I'm sorry, -1, I have -3, -2. At 0, I have -4, 0. At 1, I have -3, +2, a little symmetry. 0, 4, and then 5, 6.
So on the graph grid, I just plot those points. X value 0, y value -4. X value -3, y value -2. -4, 0. -3, +2. 0, 4, 5, going up to a 6. Alright, so I draw my curve best I can. But the flow of the graph is important here, right? Because the movement along the graph goes in the positive direction based off t. So I put little arrows on this graph indicating the flow. Same idea, except we're working in degree form. So your choices are to put your Desmos into degree mode or convert into radian form. So this would be pi over 6. That's going to be the easier approach. So 7 cosine pi over 6 t comma 7 sine pi over 6 t minus 16 t squared plus 2. All right. On the given domain of 0 to 3, this time it's going by half units. So when I duplicate, I'm going to call this, if I get back to the beginning, again, g of t, f of t, something of t. P of t, p for projectile. I've been using g of t, so I'm going to do that. All right, and then I would say g of some constant value c, for which I'll create a slider, and have that slider go from 0 to 3 in half units. All right, just making sure that it's on. So I have some points here. Going to get a little bit closer, so 0, 0.5. 0.5 goes a little far down the line here, so it looks like we're going downhill pretty good. So 0, 2 at 0. 3.031, negative 0.25. 6.062, negative 10.5. 9.093, negative 28.75. 12.124, negative 55. 15.155, negative 89.25, and then the last one, 18.187, negative 131.5. All right, so to create a graph out of this, and contextualizing what on earth this projectile is doing and under what circumstances is a different story. But clearly it's going below whatever the horizontal is, but the horizontal would not be some sort of dense material, so we just have to play that out. But if we're letting this again be the x-axis, this be the y-axis, then we're talking, in terms of the scale here, we need to go out in x around 20 units, and y I need to go down almost, if I'm rounding, 150. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That works. So go by twos. and then 1, 2, 3, 4, 5, 6 down. So that 25 should work. So 0, 2. I mean, it's going to be pretty close to the x-axis. 3 and change, negative 0.25. 6 and change, negative 10.5. 9 and change, negative roughly 30. 12 and change, negative 55. 15 and change, negative 90-ish. And then 18 and change, negative 130 something or other. So like something along those lines. Miss it, make the point bigger, as always. And the flow would have it going in this direction. And again, this is a contextless situation, so don't go by the crazy numbers. It is what it is.